Time to start. No, still 1 minute. Okay, interrupt me, ask questions. This is why I'm here, to talk to you about in-memory stuff. And I want to learn from you if you care or you don't, or I think you care because you're already here, right? Okay, I'll start my timer. Let's go. So it is kind of like a good thing to see so many people here. And usually I don't like to talk about my stuff. I want to talk about the stuff that you guys care, right? And I'm trying to understand what kind of people usually go to this event and what they want to learn. So I'm thinking about the audience, and I have a couple ideas that who you are. So we will try to do like this stupid thing with raising hands and stuff. So how many of you Java developers here? Woo, that's great. How many of you architects that looking for low latency projects? Architects, where are you? Nice. So we have some NoSQL guys who likes key value stores, no joins, no tables. Awesome. First time here this IMDG thing. No, I'm not. You can, it's okay. And how many of you guys here because you love data? Great. Okay. So let's start. Who is this guy? Who knows this guy? Yeah. This is Ivan Drago from Rocky IV, but the actor, this is sort of fact that usually people forget. The actor, Dolph Lundgren, has actually Master of Chemical Engineering from University of Sydney. So this kind of close enough, right? Okay. So yeah. Okay. So I'm Viktor. I'm talking to people when I work as solution architect in Hazelcast. I speak in the conferences. So this is what I do for money. This is what I do for my joy. So this is why I'm here today, to talk to real people. And I also wrote the book some time ago. It was JavaScript book. It's still a good book to read if you are enterprise world and you're trying to convince your boss that you need to write HTML5 applications. It's a very nice place to start. Okay, so enough about me. Let's talk a little bit about agenda, what we're going to talk today. It's not going to be like a product pitch, even though I'm from Hazelcast. I'm not going to tell anything like specific to Hazelcast or any others, the data grids like Oracle Coherence or Apache Geode or any other. I'm going to keep this talk is more or less neutral because many things that I'm going to talk today is more conceptual, and you can find these features or add some sort of type of implementation in many products. So we're going to talk about the landscape, like where in-memory data grids or where in-memory technology right now in terms of technological landscape. We're going to talk about the applications where you can apply this knowledge about the in-memory data grids. And we're going to talk about the different topologies, how they work, how we preserve data, how we achieve high availability, how we achieve scalability, and etc. And I have this like specific time slot for questions, but as I said already, if you have some questions and I can answer them quickly, I'll do it during my talk. Otherwise, I'm going to do it on the QA session. Okay. So let's try to define the problem, right? I shouldn't start with the problem. I should start with something more inspiring. But as I understand, we have Java developers here. And many Java developers run their application in JVM, obviously. And many problems that we might face is that comes from the platform. We sort of used to these problems, and we know how to live with these problems. And from this slide, I like this slide in particular that shows you in one picture that size of your data matters and speed to access to your data also matters. But you cannot stay on one place. You cannot achieve both, like have like high speed and put a lot of data. You need to invent different things. So we're starting with the basic situation, right? We're starting in the memory of in-process memory in the process of your Java virtual machine, Java heap. Java heap, this is the way how we can limit or maybe protect the operation system from going far beyond from the memory. So we can actually limit it with size of the heap. So the heap, this is the place where everything starts. We're storing our data, our objects on the heap. And if you're not doing some crazy things, usually the access to these objects is fairly fast. Also depends on the hardware, etc. But we used to say, like, if it's like map and memory, access is almost instantaneous. When you're starting putting more data in your application, you need to more memory. So, and you find yourself in a situation when heap is not enough, right? If you can do like a bigger heap, you can start facing the problem of garbage collection because you can address more memory, but you will face with more side effects of it, right? So you sort of create more stuff, but garbage collector needs more time to collect some things that you created, maybe not intentionally. It then will take more time. So you start thinking about, okay, so I need to allocate memory outside. So we start talking about different technologies that provide you access to off-heap data. And Java 9, for example, they will introduce the API called Project Panama that will allow you to avoid these unsafe hacks and get access to off-heap data structures natively. But for now, we need to use these hacks with Java unsafe. And how many are you using unsafe in your little life? That's good. That's good. We have not many people here because it's unsafe. Now, so some of the applications can actually overflow content of the heap into the disk if they're running out of heap. But with overflowing, as you can see, like we can store more and more data, but the time access to this data is going down. So when we start dealing with disk, or we need to dealing with some external storages, we're still facing more and more problems, like in terms of we can address more memory, we can store it in database, in the file, on the HDFS, distributed Hadoop, the file system, etc. But the time for accessing this data would be less than if you would access it from the memory. So what we need to do, this is like a very enterprising slide, right? How many of you can see in your life, like maybe another day, right? Enterprise architecture. Okay. This was a slide of one application, right? But in real life, we're dealing with multiple applications, and the way how we scale and how we dealing with this demand of growing capacity, we need to add more machines. But in this case, we increase the load for database. We need to come up with ideas how we scale database. I'm going to talk about this a little bit later. But this kind of things that I think most people struggling right now, right? When we do with Java and Java-like applications. As I already said, we have these constraints of heap limitation and garbage collection process. Because heap is limited, you limit your heap during the startup. There is no way how we can proactively increase the usage of this memory in terms of when you have like a peak loads. And because everything runs within operation system, some rules also operation system rules applies. For example, swapping of the data goes from the memory into the disk, and this process for bringing data back will also affect the performance of the application. We can run multiple applications. Usually we run multiple applications on one machine. So in this case, the context switching also causing some problems, another problem, causing some of the time, right? Maybe it's not super visible in most of the applications, but it is what it is. So we have this thing that we sort of cannot do anything. And accessing database and leveraging like network I/O. This is kind of stuff that we see like every day. Like um, the problem usually with databases, you're trying to scale your database by introducing a replication. With replication, you sort of some of the piece of data dedicated for reads, some of the piece of data dedicated for writes. But I'll talk about replication in a couple more slides, and I show you that it's not super scalable for obvious reasons, because you can scale within like one machine basically. You need to grow resources on one machine, because in the replication scenario, your size of your data is guys, come on in. There's plenty of seats here. Don't stand there. Uh, so when you do a replication of the data, your data is constrained by the size of your smallest machine in your replication cluster. We're going to talk about sharding a little bit in a couple more slides. And new trends. We on this conference. The conference usually brings some pioneers, some of the innovative people, and year after year we're talking about some innovative technologies, and like we're talking about new best things. Like a couple of years ago, we were stuck with some like fat clients, swing, flash, etc. Right now, all our application, mobile, HTML5, etc. So this thing is constantly changing, and your application needs to address this demand, and come up with some universal solution. As you can see, I remove multiple layers from here because they are non-essential. And right now, your phone is much performant than some computers like 5-10 years ago. Now, universal data transfer solution. Is it IMDG? Is it in-memory data grid? I'll try to answer this question in the rest of the presentation. So do you guys have any questions so far? Everything is clear, like we screwed with a problem, right? So now we're done with problem. Now we're talking about nice stuff. Okay, so where we are today in terms of positioning in memory data grids comparing to other products. So everyone, every project, every application uses some sort of persistent storage. 80% is the SQL databases. Oracle, MySQL, Postgres, and this is why this takes more of the space, right? And to communicate between multiple components of the system or multiple applications, we usually leveraging some messaging patterns. We're introducing messaging middleware, MQ series, ActiveMQ, RabbitMQ, other. To do some processing, we can use some of the in-memory computing technologies. And the way how they overlap, it actually means that they sort of have some sort of similarities all the way to integration. So for example, messaging middleware overlap with SQL databases because some of the messaging middleware use SQL databases to do a persistent storage, right? So they actually writing into database if you need to do durable messages. Say again? Yes, I do. One is for sound. Exactly. Yeah. And they overlap like similarly. And a couple years ago, we see the rise of NoSQL databases. They're eating a huge chunk from the SQL guys, and because it's convenient, right? It's convenient and fast, and they removed some of the constraints that brought the SQL database brought us, and it's much easier to use or much easier to scale. So, and from the perspective of this, I think we somewhere in between, like the technology that we're talking about in memory data grids, we're somewhere in between. Because if you look at some of the products that implement this technology, some of them have similar aspects of any of these technologies that we already know. Some of them provide the interface for doing SQL queries. Some of them, most of them provide interface for doing non-SQL, like a key value access. in-memory grids provide APIs to do messaging in memory without introducing the third-party tools. And obviously, once the data inside the grid, it would be wasteful to bring this data somewhere to do computation. So in this case, they also have ability to do distributed computing. So there's some use cases or some of the applications where current the products, they actually strive, and huge success might achieve by introducing this this type of things. So cache as a service, this is most common, like 80% of the users, they think about, if they introducing in-memory data grids in their projects, they think about distributed caching. Because they think about caching, they know the cache, this is storage that allows them to access data that hot much faster than fetching it from the underlying resources. But these resources might be heterogeneous, right? So one application can work with multiple databases, or one application can work with multiple databases, web services, mainframe services, and etc. So the cache as a service is a concept that allows to bring some sort of like unified storage that bring data from different sources and unify the access pattern. Either the NoSQL key value access, or you can use SQL-like things that you used to do in SQL databases. Application scaling. Because of the APIs that the in-memory grids provide, for example, for Java developers, this is very compelling. This is very nice thing to use to do my own application scaling. So I'm developing the product, and I want to introduce some HA concepts for that, right? And because of the nature, the memory grids, it would be very easy to integrate it with our own application and make our own application as the cluster member, and they use this solution to do clustering for our own application. Database caching is kind of similar to cache as a service, and as I already said, data already in the cache. So there is no need to bring the data somewhere else to do computation, especially have terabytes of data stored in your cache. So the grids that allow you to execute the piece of computation right next to your data. And I talk about this in a couple more slides. And obviously, demands of accessing this data should introduce new types of clients that don't need to be configured to know about topology of the cluster, topology of the grid. So, how many times you bring in new memcache, server, you need to restart your application because you need to change the configuration. So your application client needs to know that you just add new cluster. So this is not the problem with current modern in-memory grids. So this is sort of cache as a service. It can be accessed from many different types. If you see this Hazelcast, most cases it's similar to other solutions. You can access the data that's stored on the grid from multiple clients. You can use these grids to do intercommunication between different applications. Application scalability. Your users using your shopping cart and some of your Tomcats or your JD servers or WebLogic servers goes down. So you don't want to lose this user shopping cart because it's a bad experience, because we're all about good experience for users. Now, because of the integrating the grids or integrating distributed cache into application, this data will not be lost. And session will be replicated across multiple application servers using in-memory grid technology. Some other use cases in terms of elastic scalability. We just need to bring more machines without configuring cluster. So the nodes need to know how to configure themselves. You don't need to bring any arbiter, like so to speak, to know like, do we need to like, do we need to register node somewhere so the other members would know? In most solutions, most data grids, they actually provide the way how you, with zero configuration, just bring new machine, it will automatically discover the cluster, and it will get this all required configuration from this cluster. Sounds like a magic, but this is the way it is. It works. Super speeds achieved by introducing, but everything happens in memory, and everything happens in fast networks. So this is why this is fast speed. This is kind of must, and we're not touching the disk. Disk is slow. Everything happens in memory. Fault tolerance, we're going to talk about this in a couple more slides. And the cloud, right now, cloud is a big thing. All people, like I have like big customers they come to talk to us, and all deploying their application in public or private clouds. This is a big thing. And the ability to Dockerize the product, Dockerize the grids, so they can be easy deployed in or AWS, for example. If you need to grow this the size of your the data cluster on demand, during Super Bowl, you see much demand, and the people are coming to website, super big loads, and with integration with cloud tools that allows you dynamically scale, this is actually a very nice feature that you can use in your applications. So another slide about how the in-memory grids can behave as intermediate of underlying sources. You have certain accesses, and your application just work with simple API, just map.get, map.put, or you can execute some SQL queries, SQL-like queries, because still it's NoSQL, so in this case it's just a key value or it's a key object, but still the queries are available. The way how it looks like elastic scalability. Everything runs in cloud, and some of the nodes, as you can see, your data represents like this. You don't think about sharding because it's boring. And how many of you guys did manual sharding for like MySQL, for example? Not many of you, but it's a good thing because just these two gentlemen can share my pain. Right? It's difficult. It's doable, but it's difficult. And what if, like in 2016, product can shard, like product can provide the sort of automatically sharding. So, and this is what the grids and memory grids do. And because of this feature, automatic sharding of your data or automatic consistent hashing of this data, we can achieve this elastic scalability. Just bringing more nodes. We store the backup of the data. Like this is like a primary data. This is backup of this data. Same here. And when this node goes down, data will not be lost because there's still one copy of the data here, and the backup of the data is here. Some of technologies like JCloud, the framework that allows you to interact with different cloud providers, is actually many providers of in-memory grids leverage this framework to be able to run inside your cloud container of choice, cloud provider of choice. A little bit about the distributed computing use case. As I already said, data already in the cache, terabytes of data in the cache. And to bring this data to the processing, you need to do some tricky stuff, like do the streaming of this data or do the load it by page. But why to do these old techniques in 2016 when you can just send the computation to the data, and computation will be data aware. Computation will be run right next to your data without additional network hoops to bring the data to the computation. So this stuff achieved with this automatic sharding and automatic destination aware. And clients need to support this. It would be bad if clients need to be configured separately each and every time, as I already said. In the past technologies, you need to configure clients. But the clients these days in many of the products, they destination aware. They know where data is because of the consistent hashing between consistent hashing of the data within the cluster. And once the client connected or client discovered, same way as the node can discover themselves, clients can discover cluster using any choice, a multicast, TCP/IP, console, Zookeeper, whatever. It is your choice. You want to use this discovery, you can use it. And clients need to know just a little bit about information, just one live node. And after that, client can establish connection to the rest. Yeah, so I'll talk about the sort of solution, right, and some of the features. But what makes it durable? Because I said we're not touching the disk. So how it can be durable, right? You can ask me. Like if everything is memory, everything might be broken. So let's talk about a little bit about the data distribution, right? So how the data distribution works within our systems. What's the patterns? So, and basically, you can recognize like two basic patterns. I already talked about this. Who can tell me what I'm talking about here? Replication and sharding. Yeah, so we have the copy of the same data across multiple machines. Now, your data kind of spread across multiple machines. So, sorry about that. Yeah. So with replication, you have a copy of the same data, and you can use the limitation here is obvious. You need to have like a similar machines because you want to have similar capacity and similar sort of limitation here would be like smallest machine in the cluster, right? How much data you can fit there. But that is not limitation for sharding. This is actually the way how the data can be spread or partitioned across multiple nodes. And bringing more nodes, they will actually leverage more and more memory. So, yeah, this is attention check. I want to understand if you're with me. I know some of you just show me, hey, you have a black screen of that. Yeah, this is intentional. Okay, good. Because it's important stuff. It's going to be happening important stuff. So the way how it works, I'll do an example with 271 partition because this is how we do it. Some of the other products like Oracle Coherence, they have 256 partition by default. It's configurable, but stick with me. This is like a same idea. So now we're starting with the when I was speaking about the sharding, when I was speaking about the partitioning of the data, and I say that systems need to do it automatically. This is how I do it, right? Concept very, very similar the way how it's done in Java concurrent hash map, for example, right? So you have the buckets of the data, you have a certain number of threads that can access this buckets at some point of time. Similar idea in memory data grids. You have this like number of partitions that can be spread across the cluster nodes. So think about the thread in concurrent hash map and think about the processes in distributed cluster. This is how the data would be stored. Data will be stored in these buckets called partitions. And when we want to bring new cluster node, we increasing number of partitions. So now you can see here we have I have here the first line. I have still 271 partitions, but they now spread across between two nodes. So we just split them in half. Now because of that we have like similar machines, so they have similar capacity with this guy. So we have some additional space that we can use to do backups of the data. So as you can see, the partitions that stored on node 2 have a backups on node 1. So if node 2 will go down, data will be still available from the partitions that store on node 2. And this kind of concept scales very well. I'll show you just a couple more slides about how it works precisely. And what the hell I want to do, the backups in memory, right? It's kind of crazy. All right, so the way how it works, you already know like we have usually 271, some other products have different number, but it's pretty much the same. And we use the concept of consistent hashing algorithm. This is also very common between, I think this kind of, the consistent hashing term comes from the Amazon Dynamo, the paper that was, many NoSQL databases were inspired. And idea is to have ability based on the some hash function, know where data would be stored. So we take the key when we do map.put or map.get. We take a key, we serialize the key, and we apply hash function. We do the mod by number of partition, and we got exactly the partition ID. So this kind of idea of the bucket where your data would be stored. And based on this key, we store this data. Same algorithm works vice versa when you need to retrieve this data. So this is why clients is always destination aware, because they know what partition is stored, what partition stores this data. So now, how this scalability works, right? I'm bringing new machine in the cluster. And what I see here, what I have here, I have primary partitions that actually holds my data. And I have some backup partitions that holds the backup of my data. And it's obviously that I don't want to store the backups of the data from node A on node A. So this is why I store the backups on node B in node C. Now I want to scale it, right? I want to increase capacity of my cluster, so I'm bringing another machine. So the way how it works, we start usually in other, we call it migration. Some other people, some other products call it rebalancing, rehashing, resharding, something like that. And we start moving data from the network. Having the same, the consistent hashing algorithm in mind, right? So we moved the data, we moved backups, and now, just one more second, now we see the cluster in the balance, right? We have some extra space that we can use for additional data, but still, you see, you have a primary data that stores on the primary partitions. Now it stores on a different node, which is okay. And we have a backups. We stored here, here, and here. So keep in mind that this is different partitions, even though they see similar color. So once this data arrived to the new machine, it owns it. Now we can use, sort of like change the color and say, this is data, this is my backups, this is data, this is my backups. All good. So this is sort of very simplified version of what happens underneath, right? Any questions, any concerns, any, no? We're good? Yes. Mm-hmm. So in this case, yeah. Yeah, so in this case, I'm not talking about database at all. It's my cluster. And the beauty of this, it's commodity hardware. You don't need to bring expensive hardware. We have a cluster of Raspberry Pis, and it can hold, same amount of data, if you're thinking about the storage. To answer your question about the performance, no, in this case, we're actually increasing throughput because we spread our partition now across more machines than we have before. And these more machines can handle more load than it was on cluster with 3 nodes. Because of consistent hashing algorithm, clients will know exactly where data is. So client you'll do map.get key 1, and based on key 1, we know it's node D that holds partition 25. It never go to node A because node A would serve another data. So when you're serving another data, you can serve another data. So it's actually adding more machines, increasing throughput, not increasing the performance. And it's actually like very good example for cloud environments when you have auto-scaling groups. You see increasing load on your application. You need to increase your cache. You see more and more data needs to be cached because more users querying this data and you caching this data. So the auto-scaling group just bring new machine to the cluster and start this Java minus jar process. And this process happens not very often. So you're not doing migration all the time because it would be wasteful for resources. You just want to make sure that you will be able to scale. So once it's done, migration done, your cluster expanded, and you can use more memory within this cluster. Yeah. Okay, so question was how we prevent situation accessing wrong data during the migration, right? So your basic question. So idea is to have, it's actually a very good question. Thanks for asking. So the way how it works, it's actually sort of like similar to transactional. I'm not saying it's more like atomic. So when data is migrating, it's actually stores in two places, right? So when you adding, it stores on the previous location and new location. But until acknowledgement from the new location would be received, only after the mapping would be resent to all clients or all members. So, but before that, if your client still accessing this data, it's not a problem. We most of the, for example, in Hazelcast, we're preserving consistency of the data, but dropping a little bit of availability. So your call would be a little bit longer. So because we're doing migration, we're not going to drop it. We're just going to wait until migration will be done. If you do put, or if you do some mutation, you do like replace. If you do reads, not a problem. It will be, and the cluster will be able to notify the client about the current state. Yeah, please. So actually, your question contains two parts. Like, what happens if there is a primary node will fall, and another question about how this distributed transaction works in these cases. So to answer like a first question, there is no primary node. So there is no master slave because we're in a free country, no slavery here. We sit on the same, we're peers here, we're friends, right? And the same with most of the situation with InMemory Grids. In particular, in Hazelcast, we don't have any master. We have just the guy who was there first. This guy just knows a little bit more. If this guy goes down, there's another guy who was after him. He knows pretty much same stuff as this guy. It's like think about this. You come to the party, you meet the host. This guy introduced you to the party, and you join the party. And host can leave, but you already know everyone. And there was a guy who came first that can take handle of the new guest and introduce him to everyone. To answer the question about the transaction, so most of the known implementation of data grid, they support distributed transactions with different levels of isolation. For example, in Hazelcast, we have two-phase commit or one-phase commit. So in case of one-phase commit, it's faster, less consistent, because if node goes down, we lose the transaction log. If it's a two-phase commit, we actually replicating transaction log, and the transaction will be executed on the other node. Is it answer to your question? So when I said about the consistent hashing, we usually when I talk about this, it's related to smart clients. So the clients usually know where data is. So there's no situation where you hit the node, the data is not there. So when we're talking about situation with the dumb clients, which not destination aware, they can hit any, for example, you under some of the load balancer or some firewall, you can expose just one, you cannot expose whole cluster to the client, which is sort of recommended way because they chat very open. But when they call this client, call this node will be router and it will redirect the request to write node, send your request. To answer your question, yes, it is how it works. Yep. Yeah. So I think this is what your Hazelcast data grid that attached to your application. This is internal structure how the Hazelcast stores the data. Remember this green cubes that I have? So you talking with data from perspective of application. You're talking only through the one API. Yeah. You can embed an application. You can run separate service. It's all about topology. It's nothing to do with API. If you want to run it within your application, that's fine. But you need to think about that how the rest of the code of application will affect your cache server if you just need to distribute it logs and do some negotiation between nodes, which is fine. But if you want to store like terabytes of data, you need to think how the data will affect your application. So in this case, you might think about having separate infrastructure. Okay? I don't hear the question about what's going to happen if node dies. So this is why I'm going to talk about this. Yeah. Great question. So the way how it can be handled is multiple approaches here. So because of the way how it's done, we can potentially have a situation when we can lose the data because the migration might not gonna finish until the node gonna die. But thanks to the ability to assign different replication factor or like a backup count, we can have multiple backups of the same data in multiple locations. So in this case, if you have a situation that 2 nodes goes down and you have a backup count equals 2, you still will be able to serve the data because data will be still available somewhere else, not only these nodes. So in particular, into Hazelcast, you can assign up to 6 different backups. Different products have the different replication factor. Backups can be synchronous and asynchronous. These guys, I'm talking about these guys. So imagine for partition here, we can store it here, here. So you have 2 copies, not just 1 copy. So it's kind of helps to solve this situation. Another situation that I see a lot of in the world, people trying to do like they're running 2 JVMs on one physical machine, right? This is exactly your case. You have cluster of 4 nodes. They're running 2 physical machines, and 1 physical machine goes down. So you're losing 2 nodes simultaneously. So the way how it can be solved. In terms of like Hazelcast, we know we have this ability to know where we're running and how to distribute the backups correctly. So we can say, okay, looks like on the same node we're running 2 Hazelcast members. So let's not put the backup here because it might be a situation when everything goes down. So let's put it on another, like you're running on 2 separate racks. This rack goes down, it happens. But in this case, with this, it's called host-aware partition distribution or partition groups that allows to adding extra knowledge. By default, the backup machine would be taken randomly, but it also can be configured. Another approach to solve this situation is just bring another cluster because it's very easy to start the clusters with the Hazelcast and establish connection between them and to simply replicate data in active-passive mode. So here we go. You have just 3 different ways how we can solve this situation. Depends on your money, resources, and time. Simplest way, increase number of the backups, little bit play around with partition groups, and do replication of the clusters. Any other questions? Since we already talked about the hardest part, you already got the idea, right? So first of all, node goes down, restoring from the backups, data will be available immediately to serve, and the backups will be replicated after migration. But your application is up, and data will be served, and everything is perfect, right? Just let's wait until migration. In real life, it happens faster because I'm clicking here. So now, you see the cluster is in safe state. We have a data here, backups here, data here, backups here and here. And we start with what we did. A little bit about scalability. Scaling up, like we're bringing Oracle, what's it like, Exadata, like machine, like super big, or like mainframe, like we're just putting a lot of beef in this machine. Or we can have like smaller guys, and they can work like a more efficient commodity hardware. And I don't have this slide here, but a couple of years ago on the Java one, we had this Raspberry Pi cluster. And we have this Lego server racks. And the people can, come to our booth and just unplug this. Just want to see how it dies, but it doesn't. And the way how it's done is because we have this like scale horizontally. But you can ask like, can we have both? Like, why we can have both? Right? Because sometimes we have bigger access to the data. So some of these problems can be solved by integrating the in-memory stuff with your existing stack, right? Because we can read through cache from your database. Who said we cannot write through cache, right? At some point we can, when you're writing into the cache asynchronously, we can offload this data to database. In this case, preserve data in database because you already know how to. We have a 25 years of experience of scaling and dealing with databases. You can save it on underlying RESTful services. When you do read through from services, you can write through service. And hot restart is another way. So many of you heard about the Redis, and the Redis have the append-only the file that can sort of provide the durability for the cluster. Same thing, most of the grids provide. Each and every node can dump content of this memory into the file and restart like very quickly without like repopulating cache from underlying database and etc. Now, another approach, remember this Hulk guy, you have a very big machine. You say, oh, I want to use all this memory. I have so much RAM on this machine. How can I use that? Well, you can try to do like a heap, do XMX 500 gigabytes. It would be very interesting. I did this before. I'm not the one who told you that it was a pleasant experience. So the way how it works, remember I talked about the off heap, right? So why we can use the off heap as the way how we can offload some of the data from in heap cache. So in this case, heap can be small and fast access because of the garbage collection will not affect, or garbage collection will happen much faster. And off heap storage can be used. And as you can see some numbers, I did it some POC with some clients. It's for particular Hazelcast. It's I don't know how other people's do. What I saw, and I thought it would be nice to share with you guys, is that effectively I want to use like 4 gigabytes of memory. I need to store like 4 gigabyte-ish data, maybe less, maybe more, because there's some other metadata overhead, etc. But if I will do on heap, off heap, I'll get much better performance in terms of application response, right? So the application response time to the data will not be affected by spontaneous garbage collection process. So keep in mind, minor part is gonna happen with nothing to do with this. It's impossible to deal with this. This is how the Java works, right? Otherwise, we just need to forget about Java and start writing in C++. In this case, we don't need to worry about this off heap stuff because we're doing the manual allocation, right? But the minor pauses, as you can see, they still they happen, but not they're not affecting performance so much. But the major pauses they do, and from the perspective of accessing this data, sometimes you have some strict SLA with your client, right? And you need to say, okay, I want to, this data needs to be delivered in 50 milliseconds. And you have 5 seconds garbage collection process. And you're breaking your SLA. And you embarrass for your clients. You need to explain why it's happening. It's garbage collection. It's the way how Java works. But they don't care, right? They pay your money. So you want to avoid this. And do we really need to talk about this? So yeah, so this actually is, there's a, how many of you know a zero turnaround company? So they have this very nice, the technological division, Rebel. They do like surveys, they do nice blogs, awesome guys. I think like Simon here, he's doing some talk. And what they did like developer survey, and some of the things that people ask, what NoSQL solution you guys using? And we was very surprised when we saw that the people using our solution, but in obviously something you can tell about the industry. So other in-memory grids can be here as well, right? So do we really need to use like the NoSQL, or we can use everything that I just showed, like use the grid as your unified access layer, the layer that you use for interacting with this underlying storage. Because of the pattern, how we're accessing this data, and because of the nature of the data, we're not talking about relational database. So naturally, people think, well, yeah, this is like cool, this is map, this is key value. It's easy to use, right? And they said, oh, all right, so what if I don't know key? So how I can do the query? And some of the people already saw this with introduction of predicates API, right? You can provide the way how you can query object based on some of the defined SQL-like queries. We saw it in the GPA many times. Why we cannot do it here in Memory Grid? So in many products like the Ignite, they also have SQL support, etc. So this is how it looks like. At least it was what year? Like last year. Now you know. Now you have it. I don't know what you're going to do with this knowledge now. If you have some question, I'm here to answer it right now. If you have some question, you can digest something. I will be on the booth of the Hazelcast booth. Also, I have a talk today. How many of you guys use Spring? Yay! Come to my talk. We're going to talk about different solutions for, not solutions, different approaches for Spring configuration. And it's going to be battle because there are some guys who love the XML, guys who love the Java, and guy who loves Groovy. How crazy is that? I'm all yours. I have like almost like 15 minutes to answer your questions, so I'm here for you. Yep. You can ask them. Yeah, we have a certain similar concept. So I would say one difference, and you think about this. So we were in open source world since 2008. We were from the very beginning. Before that, Apache Ignite was the commercial product. They donated to Apache and started doing the stuff with open world. Maybe open source gets the traction and the people seeing the benefit of bringing people in community. I think this is, we were there. You know, our community, our power is our community. We have like over 100 committers. They not work for Hazelcast. They just, you know, eventually coming with patches and stuff, right? I don't know. Like they can tell you difference. We have they have this you know, chart with the features. But do you really need features that they need, or you care about quality of the features that you care? There's something about this. I'm not I'm not trashing about our friends. Yeah. Yeah, the question was how to deal with lazy loading of some data, and the way how it works. It's just a matter of configuration. So if you want to do some, if we're talking about some details, in details, there is concept of map store. There's actually writing and reading to database, map store and map loader. You can simply configure, say, it lazy. So in this case, it will only fetch the data that you need at the moment. Or you can do eager. It will bring everything. Or you can say lazy and manually supply set of the keys that needs to be stored in the cache. So this kind of luxury for configuring is available, and it's done. Absolutely, yeah. Like the concepts with read through cache and write through cache. This is what or you can use the client to just pump data to the Hazelcast. Same way, because the client also destination aware. Client can use a synchronous API if you just need to just load the data, and you can have some. You can sort of attach this, like the pumping data, to some external, maybe ETL tool. They do some processing on the database, and after that, you just want to pump this data in one shot into the grid. It's another option. So there's multiple ways how we can do it, but if you're asking about the Hazelcast, it's on our documentation. There's just simple configuration tag, eager versus lazy. So we're not providing any like direct integration because it's difficult, because we need to deal with object relational mapping, right? Because we're storing objects, we're storing tables and databases. So that's why come up with some the common solution that will work everywhere. It would be a little bit ugly, and we're forcing people to use this. So we did different things. So you need to sort of wrap your existing code. You already have your code for Oracle. Why are you throwing away? You don't need to throw it away. You just need to use this code to implement interface that Hazelcast will delegate calls. That's it. Just one interface: create, update, read, create, read, update, delete, CRUD operations, and your code stays the same. We're just bringing data not to application layer, but on the data layer, on the cache layer. Yes. So the Hazelcast is a Java application, and the cluster runs in Java. However, we open source our .NET clients because we introduced the open client protocol. So what it does is it's well-defined the way how the client interacts with cluster in binary form. And our .NET is available in Nugget. You can use it. We have a bunch of clients that they use Java applications and the .NET application together. We support serialization. It's called the portable serialization format. So your Java object can be accessible from your .NET and vice versa. The portable also supported in .NET, C++. We recently just released the first alpha version of the Python client, and we're working on .NET or the Node.js client. Yes. Yeah, the question is how the network technology is important. Yes, it is important. However, we're not related to any underlying, like InfiniBand, for example. If this technology provides the network stack to operation system, we accessing this network stack through the Java. We're not doing anything special to make it faster in one networks and make it faster on another. We're just using Java and IO to to get the TCP IP. We work on TCP IP layer. If you're talking about just absolutely. If you have like a faster network, it would be much better. Also, you don't really want to deploy cluster in how to say in WAN area, right? If you have two data centers, you don't want to span your cluster, because cluster is all about like a fast data. So that's why the members, they talk to each other. Like there is always some network chat happening, like heartbeats, etc. So in situation, if you deploy a cluster within WAN, latency would be so high, so your cluster will be falling apart all the time. So we have the ways how to resolve unintentional network problems, like if you have a split brain situation, like some cluster fall apart in 2 clusters and how it merges back. We have the ways. But in terms of network latency, if you have a faster, give us faster network. If you don't, we can figure out, because there's configurable the heartbeats, configurable parameters that allow to, sort of live in unstable networks. So if you don't have any questions now, thank you for your time. Thanks for coming today. And if you have some questions, I will be in the Hazelcast booth or on my Spring configuration bottle. Thank you so much. It was awesome.